We have a linear system, x plus y minus z equals 4, 3x plus 2y plus 4z equals 17, and negative x plus 5y plus z equals 8. Let's call this top equation 1, the middle one equation 2, and the bottom one equation 3. For the matrix rows, we'll call equation 1 row 1, equation 2 row 2, and equation 3 row 3. We have the coefficients 1, 1, negative 1, and the sum 4, 3, 2, 4, and the sum 17, negative 1, 5, 1, and the sum 8. The goal of Gaussian elimination is to get the matrix in row echelon form, where we have 1s in the diagonal and 0s below it. In our class example, we took this path where we went 1, 0, 0, 1, 0, 1. But this time, we're going to use a different pathway. Let's go! Notice the number in the upper left-hand corner of the matrix is already a 1. Yay, that's one step out of the way. So let's eliminate the 3 by turning it into a 0. To do this, we'll need to add negative 3 times row 1 to row 2 to obtain a new row 2. If you're anything like me, you'll want to record the result of the multiplication property of equality somewhere so that you don't have to hold those numbers in your mind. Once you've multiplied negative 3 times row 1, you'll need to add it to row 2. The resulting sums are 0, negative 1, 7, and 5. I'm showing the process steps here of adding the two rows together to obtain the new row. You can see we get 0, negative 1, 7, and 5, just like I mentioned before. You don't necessarily have to write those steps down because we usually do those mentally. Our next step is to rewrite the matrix with our new row 2. Row 1 remains unchanged. Our new row 2 is 0, negative 1, 7, and 5, and row 3 remains unchanged. Now we have a couple of different options, but I want to look at this left-hand corner. Let's make this negative 1 a 0. Now remember that the sum of a number and its opposite is going to be 0. So we'll take row 1 and add it to row 3 to obtain a new row 3. And the sum of row 1 and row 3 is 0, 6, 0, and 12. So again, we're going to rewrite the matrix with our new row 3 of 0, 6, 0, and 12. Remembering that our first and second rows remain unchanged. The route we took in my class was to multiply the second row by negative 1, but now let's make this 6 into a 0 instead of going that other route. Remember, to obtain a 0, we want the sum of opposites. So we're going to take negative 1 and multiply it by 6 so that when we add it with 6, we get 0. Translating that into our notation for row operations, we'll have 6 times row 2 plus row 3 will yield a new row 3. And just like before, I'm going to keep track of what I get when I apply that multiplication property of equality to that second row. And once again, I'm just going to show you those process steps for adding 6 times R2 to R3 to obtain our new R3. Which you can see is going to be 0, 0, 42, 42. So now let's rewrite that matrix where we have rows 1 and 2 both remaining unchanged and our new row 3. Our second to last step in achieving row echelon form is to turn this negative 1 into a positive 1. Since the number already has an absolute value of 1, we just need to change it to its opposite. So we're going to multiply row 2 by negative 1 to obtain a new row 2. And when we rewrite our matrix, row 1 remains unchanged. We have our new row 2 of 0, 1, negative 7, negative 5, and our row 3 remains unchanged from the previous step. And for our last step, before we achieve row echelon form, we need to turn this 42 into a 1. Remember, to turn something into a 1, we want to multiply by the reciprocal or the multiplicative inverse, which is the same thing as dividing by itself. So we're going to have 1 over 42 times row 3, and that will give us our final row 3. And after all of those row operations, we have our final matrix in row echelon form. Our equivalent system of equations is going to be x plus y minus z equals 4, y minus 7z equals 5, and z equals 1. Now we're going to use back substitution to find y and x from z. When we substitute z into the second equation, we will end up finding the value of y, which is 2. And then we can substitute the values of z and y into the first equation, and when we simplify, we get the value of x to be 3. So the solution to our system of equations is 3, 2, 1. And I verified that solution with technology, and that is it. That is using Gaussian elimination step by step. Wow.